The world is producing data at an unprecedented rate, faster than our ability to analyze and understand it. Within every Intel chip manufacturing facility across the globe, innovators are pushing the limits of science and literally rearranging atoms to create groundbreaking technology.
What's up, everybody? I am Abhishek K. Sharma, volunteer from your beloved team, Team MetaMorph, NIT Hamirpur, NIMBUS. And this fine evening, we are back with a guest talk from our guest, Dr. Aditya Morey, sir. Now, I would like to ask Tanya to assist me introducing Sir to our audience.
Thank you, Abhishek. Work hard, do hustle, face failures, explore things, and make it happen. Today, we have Aditya Morey with ourselves, who stands as a perfect epitome for previous sentence. He pursued his graduation from IIT Kanpur in the field of material science. Then, he went to Northeastern University for his master's in material science and engineering. Initially, he done his research work on superalloys materials in DRDO.
Then, in 2015, he must have some great intentions, which led him to develop a school named Angelica International School for poor students where they are taught great business models free of cost. Currently, he is employed as product development engineer at Intel Corporation in California, United States. Apart from these produced sort of tasks, he holds many fantastic talents about which we are going to learn into this session.
Now, I would like to call upon stage CC of our team, Rahul Bhatia, for a welcome note to Aditya Morey, sir.
Thank you so much, Tanya and Abhishek. Hello, everyone. I, Rahul Bhatia, CC of Team MetaMorph, welcome you on the behalf of my team for this event. Now, I would like to invite Mr. Aditya sir on the stage. So, thank you so much,
Hi.
sir, for joining us.
Hi. Thank you for having me here. Thanks to you guys and hi to everybody at NIT Hamirpur. So, thanks for the lovely introduction, guys. My name is Aditya, and I work as a product development engineer here at Intel in Santa Clara, California. And I'm here to give you guys a small talk about things about material science, about mechanical engineering, about things about your careers, and some very important tips and a lot of things that you guys might not have heard so far. And I'm sure I'm not going to give you a lot of science because I'm sure your professors teach you very well. Good material science, good
Yes.
mechanical engineering. So I'm not going to throw a lot of science at you guys, but on the other hand, I'm going to help you answer some questions that students generally have as to once I have finished my graduation, what do I do next? Do I switch fields? Do I not switch fields? Do I continue in material science? What are the job prospects? What are the salaries? Because these are things nobody's ever going to tell you. Nobody's going to tell you their salary, right? So, what are the most important and pressing questions in the fields? And if you're looking into research as well, because I have been on the spectrum from right from research to industry to lab work, as well as pursuing a PhD, as well as working in a startup, working in an NGO, as well as working in a very large corporation like Intel. I have worked in India, I have worked in some African countries, I have worked in Europe, and now I'm here in the US. So I think I'm at a unique position to give you guys a global perspective as to what are the realities of different things. Some things they might not look very good, but they are really good for your career, and some things that look extremely glamorous might not be the way they seem. So let's get started. So I do have a presentation prepared.
Yes, sir. Sure, sir.
Yeah, thanks for pulling it up, Tanya. So just a few introductions. I just gave you my introduction. I'm a product development engineer at Intel. So at Intel, what my job is I do pre-post validation of silicon dies. We will get a little bit more into details later on in the presentation. But most importantly, what we do is once the silicon wafers are created by the fabrication units, which are our factories, they're located in Arizona and Oregon here in the United States. We here in California receive those dies. They are cut up into little sections that later become computer processors. And we use high density testers called HDMT testers to send our programming code into those dies and ask it a bunch of questions. Let's see if an OS can load on this. We try to see if it can answer a simple math question, right? So we use programming languages and lots of different tools and electricity as well to send these questions and send these electrical impulses to these die, and then we see what kind of response we get. And this procedure is called sort. So I belong to a larger organization under Intel. It's called the Manufacturing and Product Engineering, or MPE. And under that, we have a huge team here in California as well as in Arizona. We're called the sort team. And 96% of all global Intel revenue goes through sort. So each and every chip, each and every processor, each and every server or client die that we sell through Intel has to go through sort. We meticulously check each and every chip that we ship to our customers, and we make sure that everything is in perfect working condition before we send it out. So anything goes wrong at sort, we might be selling a bad processor or a bad die to the customer. So, and that harms the company. So that is something we are not willing to do. And we test each and every die very meticulously, and that is the most important thing, I think, behind validation. And this is a word that you'll hear a lot when you go ahead in your careers, go into jobs, is validation. Validation and quality control is something you will hear a lot, especially in material science and mechanical engineering. Wherever you go, be it in the medical field, be it in the semiconductor industry, obviously, or be it in any kind of manufacturing industry, quality control and validation is something you will hear a lot. And this is something you need to get into a habit of right now before you become engineers, real life engineers. Right now, you guys are all students, but when you become real life engineers, these are the things that you will be focusing on. I have recently joined the semiconductor industry. In the past, for many years, actually, my work was focused in the medical device and research and development. So I was working mainly in the medical field, building products, building implants that go into people's spines, building catheters that pump people's blood. So these are the things that I was involved in. I was also involved in a lot of stem cell research, a lot of biomaterial development. And so and the names of the companies and institutes that you see at the bottom are some of the institutes and very esteemed places that I've been associated with, or I have worked on. Intel, BRC, Stanford, CCMB. These are places whose products I've worked on, whose people I have collaborated with. And as we go later into this presentation, you will see how important it is to associate yourself with important institutions. Okay, next slide, please. So this is going to be a basic roadmap as to how this presentation is going to go. First, I'm going to talk a little bit of more detail about silicon and semiconductors and medical devices. Then we'll talk a little bit about mechanical engineering, and the most time that I'm going to spend is going to be on the last part, which is the future, as in what are the future aspects, what are the most important questions that students have. I have been actively helping a lot of students get admits into the US go to grad school here, MS, PhD, as well as I try my best to guide students and people who reach out to me on LinkedIn or through other platforms in order to secure jobs, increase their pay, and many such things. So those are the things that I think you guys should mostly focus on from this talk. So you should be looking forward to that section the most. Yeah, next. So basically silicon and semiconductors. Okay, so this is a very simple overview as to what happens, especially at Intel and most other semiconductor companies like TSMC or AMD does the same thing. First thing what we do is design. We have chip designers and chip architect, SoC engineers. They meticulously design each and every small transistor that goes into a chip. So if you guys know the working principle behind a silicon chip, is that a silicon chip basically works on transistors, and transistors are these very small units of boolean value, which gives you true or false, 0 or 1, on or off, right? So when you pass current through a transistor, it can either give you a 0 or it can give you a 1, based on what kind of current you're passing, or based on how it is linked to the entire circuit, right? So the the advent of the transistor has brought technology from being computers being size of rooms to being the size of a cell phone that is in our hands, right? So the material that has made this possible is silicon, and silicon, out of all the materials, we use silicon because it is a group 4 element. It has 4 electrons in the valence shells. Like, this is basic chemistry, right? It has 4 electrons in the valence shell, just like carbon, right? And silicon is the most abundant element on the earth's surface, silicon and oxygen, because it is found in the form of silicon oxide, right? SiO2. So and it is found everywhere on the earth's crust, which is basically sand. So we take sand and we convert it into silicon. We remove the oxygen. Basically, we reduce it to pure silicon, and then it goes from there. Once we have that pure silicon wafer, our design engineers make those. They literally draw those designs onto it, which are the mappings of the transistors, all the pathways, all the gateways, all the cores of the processor, and memory, and different parts of it. Next, it goes into the factory, which is also known as a fab. This is a class 10 clean room, which is a huge complex. It's a huge facility which has moving robots. It's pretty cool. You should look it up online sometime. There are people wearing bunny suits, which and that air inside that fab is cleaner than the air inside operating theaters or operating rooms. So it's a class 10 clean room. So in every cubic meter of air, there will be less than 10 particles of dust. So that's how clean it is, because we cannot afford to have even a single nano-sized dust particle on our silicon. Next, this silicon goes through processes like mask operation, lithography, photolithography, chemical etching, chemical and mechanical planarization. All these steps are only to build layers on top of the silicon and to make those connections. And if you guys have studied thin films, or if you have studied a little bit of electronics, you should know how these processes work. I won't go too much into the science. Next, once these chips are created, once these wafers are created, they're about this big. They're called silicon wafers. They are round. Then it comes to us at sort, and we meticulously check. We write programs, we write algorithms, we develop data analysis tools to check each and every die meticulously, and then we go from there. Once we have a set of good die that are working, we have a set of good processes that work, we send them off to assembly and test. So there's where you take a substrate, you put the silicon on top of it, and they have a heat sink on top of that. That is the final thing that you put in your on your motherboard. That is your processor, like an Intel i7 or i9 processor, right? That is called a package, and this process is known as packaging. After the packaging is done, one final test is done by the assembly and test team. They just put it on motherboards and see if everything works, and after that they go to warehouse and are shipped to our customers. So this is basically a small overview of how the silicon and semiconductor industry works. But let's dive into a little bit into the details, right? Next slide. So like I said, it begins at sand, the most abundant thing. It's literally free. So there is no capital investment as far as acquiring sand is concerned. And then we use a process known as the Chosalsky process, in which we reduce the sand first and we get molten silicon. But this silicon is polycrystalline, right? It is molten and it can have grains in any direction, right? We need to make a silicon single crystal. So we use a seed crystal and we dip it into the molten silicon and we start pulling it out. And once we start pulling it out, it forms an ingot like a cylinder. And the thickness of the ingot depends on how fast we are pulling it out and how fast the silicon is crystallizing on the seed crystal. So based on these factors, it is pulled at a certain speed so that we get the size of a die, the diameter of the ingot. Once we get the ingot, they are known as silicon ingots. They are used. We use diamond cutters to slice them into very thin wafers. As you can see in step two, then those undergo a lot of cleaning, a lot of polishing, and then comes the lithography steps that I was talking about. So you have to appreciate how far technology has come. There was a time when before silicon, the transistors were about this big, and computers were the size of buildings, and they had only 5 MB of space. Right now, the intergate gap between transistors in an Intel chip, we are at 7 nanometers. So we can have as many as a billion transistors on a chip that is about 1 inch square. So 1 billion transistors that do many flops of zeros and ones. And these zeros and ones are your images, your text, your videos, all your streaming, all your content, and your access to the internet, everything. Everything is in terms of binary, zeros and ones, that go through this processor and is displayed on a screen or converted into audio signals. So this processor has to do a lot of work, and we cannot make the processor any bigger. So Intel believes in something known as Moore's law. Gordon Moore, who was the founder of Intel, predicted that the number of transistors on a chip will double every 2 years. And we have been seeing this trend so far, and Moore's law is working. They started with 32 transistors on a chip, and right now we are at over a billion and going strong forward. In our next iteration, we hope to achieve chips that have the node gap of almost 3 nanometers, and we also have for 2025 we have plans of 1.28 nanometers. So that is going to be the limit of Moore's law. You cannot go closer than that, because that's pretty much the size of a silicon atom. You cannot make things go closer than the size of the atom itself. And after that, then we'll have to think of something else. Maybe, I don't know if you guys are knowing about quantum computing and how we use qubits at sub-zero temperatures to process data. And that seems like the direction to go forward in. That is the future of computing, which is known as quantum computing. And there are top people working on it right now, but that doesn't seem like a reality anytime soon. Maybe 10-15 years, but so far this is what we have, and this works very well. uh, Intel processors support almost billions of computers all over the world, billions of cell phones, as well as a lot of server chips. We also make server chips. So large data centers like Google's and Amazon's have servers which run their data, store their data. So Intel chips are the ones that run that server. So the largest cloud service in the world, which is AWS, Amazon Web Services, they run Intel chips. And a lot of money and a lot of services are depending on these servers. All of Netflix is hosted on AWS, all of Hulu is hosted on AWS, right? They're multi-billion dollar businesses that rely on cloud, and cloud is supported by hardware. So even if we think that software is the future, cloud is the future, definitely, and being virtual is the future, there is kahin na kahin, there is some hardware somewhere in some part of the world that is crunching the numbers, that is doing the math, and most likely there's an Intel chip behind it. So basically, overall, this is the process. Now let's touch other topics. So again, circling back to what I used to do before getting so interested in the silicon industry, is medical devices and biomedical engineering. So what I used to do before this, these were the main focus areas of my life. They are biocompatibility, biomaterials, nanotechnology, and developing new products for top companies, right? So what is biocompatibility? Most important thing to understand is the human body is very sensitive. You put any foreign object inside the human body and expect it to heal around it, that is not going to happen. There is a very small subset of materials that can be allowed inside the body, and even they are not perfect. And as biomedical engineers, as material science people, our job is to go towards perfection as much as possible. The materials that we know for sure are very biocompatible. Stainless steel, that's why we use stainless steel rods in orthopedic surgery. Titanium, we use titanium in dental implants, we use titanium in orthopedics, right? And a lot of materials known as hydrogels. So these are basically polymers that have a capacity to hold a lot of water. So hydrogels, different kinds of metals, different kind of ceramics like zirconia, uh, aluminum oxide, right? So these are the kind of materials we use in the industry to make implants. So next thing is nanotechnology. Nanotechnology basically is any technology that works on the 10 to the power minus 9 meters length scale, right? So if we are able to create a texture that is that small, if we are that changes the hydrophobicity, that changes the surface energy basically, right? It changes the water contact angle, right? Once we are able to change that, my research has found that if you have the ability to change the contact angle of a certain surface, you are able to change its biocompatibility. So basically now we can tailor make any substance and make it biocompatible. We can increase or decrease its biocompatibility according to the need that we have. So recently I have developed spinal implants using 3D printing, which is an additive manufacturing process. I'll get into that a little bit later. And then I have used certain techniques of mine, which imparted a nano texture on top of these implants. And what we found is when these implants are put inside a clinical setting, like inside an animal or inside a human being or around cells, like in an in vitro test, uh, they reduce the number of bacteria formation, they reduce post clinical infections, and it increases cell adherence. The number of cells growing on that and engulfing it into the body without causing an infection, that is very high. So this was at least for my career, this was a very big breakthrough, and it was brilliant. And out of this research and similar research, I have filed 8 patents in the last 6 7 months, I guess. And it has been extremely rewarding. So this is one area of science that is progressing very fast, and I would seriously urge you guys to take up a career in medical devices, biomedical engineering, and biomaterials in general, because it is a very rewarding field. And at the end of the day, what motivates me to work in this industry, and I still do a lot of my background research, even though I work at Intel, a lot of my background interest and research still goes into medical devices. What's most important for me is what motivates me in this industry is, that your work someday somewhere is going to save somebody's life. Whatever work you do today in a lab is going to translate into a product, and a company is going to launch that product, and that product is going to go into the hands of a surgeon who is going to use it on a patient, and that patient is going to go home to his family, to his mother, father, husband, wife, right? And that person is going to have an extended life because of the work that you do. And I think that is the most important motivating factor in this industry. There are some other there are reasons why I have decided not to work in this industry anymore, which we will get to. So stay tuned for that. Next slide. Yeah, so as I was saying, the materials that I developed were developed using 3D printing, and this is a list of patents. So if you guys have access to this presentation, you can go look them up on the United States Patent Registry website. Okay, these are the patent numbers and titles. So basically, what I did is we used metal 3D printing. So 3D printing has has been around for the last decade or so, I guess, at least in terms of ABS plastics and PLA plastics and PEEK and lots of other polymers and plastic materials. But in the last 5 7 years, what has come around is metal 3D printing. We have come up with binder jetting. We have come up with selective laser melting. Oh, I have a question here. What is the next flagship processor going to be? Okay. So at Intel, we have internal names. And the marketing team decides what their market names are going to be, like i9, i10, or whatever. So internally, I know the next server chip that I'm working on is called Granite Rapids. You can read about it. You can just Google Intel Granite Rapids. So we are making these server chips that will help take up the load on data centers and servers. As far as computer chips are concerned, I think we'll have the 13th generation i9, which is called Alder Lake. We did release a family of chips that are competing with Nvidia right now. I think they are going to release next month. They are basically not chips; they are GPUs. They are fully dedicated GPUs. So this is the first year Intel is coming into the GPU market, competing directly with Nvidia. So yeah, it's going to be very interesting. They're called Intel Arc GPUs, I believe. So I'm not very familiar with the market side, what they call them. Sometimes they call them i5, like the small core processors called i5s. Is Intel company searching for new material for chips? Interesting question. It's a very good question. We have been searching for materials for God knows how long, but the science is there, right? Only group 4 elements can be used. Why do we use silicon? Is basically silicon has octahedral voids, right? When those four atoms form a lattice in silicon, there are voids, and those voids can be doped. Those voids can be doped with group 3 or group 5 elements like aluminum, boron, phosphorus. Once we do this kind of doping, we can change its conductivity, and once you change its conductivity, you are able to change if it's on or off, and that's what basically makes a transistor. So there is hardly any other element that can be used for this purpose. Now within group 4 also, if you search carbon, it cannot handle temperature, it will just burn off. Next is germanium. Germanium is pretty much liquid. After like it's a very soft solid, and after that whatever comes below germanium is I'm pretty sure is radioactive. So what we are left with is silicon, which is the sweet spot. It is neither, it can handle high temperatures, because when current flows, things get hot, processors do get hot. That's why we have so many cooling solutions, right? Water cooling, air cooling, all kinds of stuff. That is because processors get hot, and when they get hot, we don't want your processor to just melt away, right? So, or burn away. So carbon is definitely going to burn away. It is going to oxidize into carbon dioxide and fly away. The only thing that can handle high temperatures is silicon. That is why we have built an industry from the last 70 years that is functioning solely and solely on silicon. And what our focus is not on finding new materials. There could be new materials. I have read research papers from people who have managed to use carbon nanotubes or graphene for making transistors. But that technology is still at a very lab level and is still not efficient. We have a making silicon chips is a well-oiled machine, at least in the US, and I think everywhere in the world. And nobody else other than the top three companies in the world can actually do it. The art of doing that is actually not even a science. It's an art of actually making those small cuts at those nanoscales. These are machines are patented by Intel. They are patented by AMD, by ASML, by Samsung, by TSMC. These are the 4 5 companies who can actually manufacture something at that scale and at that quality. So it's not easy to do. So the innovation, where it comes in is, innovation comes in at chip design. Make better designs, make smaller transistors, make better technology to make smaller nodes. So we are focused on making better machines to make these chips, because we know silicon is not going to go anywhere, right? Okay. So coming back to 3D printing. Yeah. So 3D printing basically is additive manufacturing. It's not subtractive. So far we have been doing subtractive manufacturing, as in we take a large piece of something and we cut away. We use turning like lathe machines, we use milling, we use drilling and stuff like that, and chopping it up into parts to make a product. Now we start from nothing and we start building the near net shape product itself. Now within metallurgy, a few guys have studied material science, right? So there is something called powder metallurgy, there's something called additive manufacturing. So right now we are the bleeding edge of additive manufacturing, at least for 3D printing, is metal 3D printing. We use binder jetting, we use selective laser melting, and such techniques to create products from powder beds. We use a bed of powder of metal, and now this powder is created using a process called atomization. I'm sure you guys are aware. So we use water atomization or gas atomization to produce these very fine, small, 50 to 100 micron sized powder particles of pure metal or pure alloy, and then we use different techniques to sinter it and to make it a near net shape, or sometimes even net shape. So selective laser melting gives you a total net shape, means it is completely ready to use. You take it off the bed, it's ready to use. No need of any kind of heat treatment, no need of any kind of polishing, no need of any kind of post processing to bring it to market or to use it in any way. So 3D printing is very important for manufacturing. Next thing is 3D printing is very important for rapid prototyping. What is rapid prototyping? Is basically making a prototype of something that you think will work and seeing if it fits. So making a quick copy of something is it helps engineers in new product development. It helps engineers decide if something is too big or too small, or if the tolerances are not right. So if you're having the power to quickly make a prototype, that helps a lot. So that helps with project management, that helps with saving time and saving money. Imagine you spent a lot of money and you bought a machine that makes a machine that makes a product, and finally you end up realizing that the product size is not right. That's a whole lot of time, energy, capital, money, energy, people wasted. So if you have a 3D printer, you can just print out the product, see if it fits into your, let's say you're making something for a car, see if it fits, see if it's right. If you think your design is perfect, everything is working properly, then start making the metal version. You just make a plastic prototype. So this is called rapid prototyping. This saves companies lots of money and time, and 3D printing has made it possible right now. It was not possible before. Another thing is customization. As far as the medical industry is concerned, uh, you cannot make custom implants through conventional manufacturing, right? You cannot ask a company to make an implant just for you because your bone is a little smaller or longer, right? Because you have a unique patient anatomy, doesn't mean that a company is going to make a unique implant for you. It's just not possible. It is just not manufacturable. But with 3D printing it is, because 3D printing at the end, the design is a CAD software, it's a CAD file. You can just make small changes to the software, and the laser will just make a new implant just for you, specifically for you. So making custom implants and making customized products is again another very big advantage of 3D printing, and that is why slowly the whole medical industry, manufacturing at least, is switching to 3D printing, and that is the future. So before starting at Intel, I started working at a startup called Printer Press. It is a Stanford based startup. So there are alumni from Stanford, UC San Francisco, and some top surgeons in the country. We started a startup, and everybody brought their expertise. The surgeons brought their medical expertise. We bring skills from the materials and mechanical side and design side, and we started a startup that which is going strong, which are $25 million in funding. Okay, I have a question. Nalin Thakur is asking how increasing threads leads to boost in CPU power. Okay, your question is basically associated with something called chip design and SoC design. CPU power doesn't increase with increasing threads. Threads is basically, threading is nothing but the number of interconnects between different cores of a CPU, right? So the number of interconnects increases, the number of data flowing can increase. That's what makes process faster. I mean, if you have a, let's say, a laptop which is using a processor, and you click the start button and you want to see how long it takes for it to pop up, is the amount of time that the amount of time the instruction has gone to the processor. The processor has understood it and then implemented it. That delay or that lag is controlled by threading. And so we do processes known as hyper threading. We increase the number of interconnects, but then that has its low side also. If you increase the number of interconnects, that increases the temperature at which a clock works, or like these things are called clocks in CPUs. So it increases the clock temperature, so that makes cooling very difficult. So there are people who overclock their computers, like overclock their CPUs and get them hyper threaded, right? They have to use something called liquid cooling, water cooling, or even liquid nitrogen cooling. Like liquid nitrogen is at minus 196 Celsius, if I'm right. So you need to go to those temperatures to even keep the CPU running. So there is a trade-off between temperature, but yeah, basically what threading does is increase the amount of data flowing within the cores of a CPU. Yeah, next slide, please. Yeah. So before going into other topics from biomedical, I would like to share the last project that I was working on. So I was working on making a hip implant. I don't know if you guys are aware. So when people have arthritis, which is a large population in the world, in the US alone, we conduct over 440,000 hip replacement surgeries every year, which is a very huge number. And as the number of aged people in the world, the global age keeps increasing. We're calling it the silver tsunami. So in the next 25 years, the number of people who are over the age of 65 is going to more than double, which is a huge increase. And these people, as these people become old, are more prone to diseases like osteoarthritis, right, or rheumatoid arthritis. So for these people lose a layer on top of the bones that connects the bones together. So this layer is lost, and the bones start having friction with each other, and there is extreme pain and joint loss, and a generally bad life. So the only way to help these people out is to remove the part of the infected bone or affected bone and replace that whole joint with a prosthetic one, which is known as a total hip arthroplasty. That's what the surgery is called, or a hip replacement in layman's terms. So what we do is we cut off the bone. We insert a this is what the implant looks like in the design section. And then we put a ball on top of it, which is generally ceramic or metal or cobalt chromium, and then we put it back into the socket of the patient. The socket is also lined with an acetabular cup, which is generally ultra high molecular weight polyethylene, and then this forms a new joint, and the patient can live a happy life. He can run and jog and walk. So I think this is really important for to lead a normal life, is to be able to move, right, to go from point A to point B. So this is what a hip implant does. So I developed a hip implant using 3D printing. So far 3D printing was never used for hip implants. So this project, or this design for a implant, had these basic steps. First step was biointegration, right? Biointegration is making sure that once that implant goes inside the body of a patient, it doesn't cause an infection. You don't have to open him up and take it out again and put a new one. That is just making the patient's life even worse, right? So we use a technique called dipping. We dipped it in various chemicals. Those chemicals are, that you can find in my paper. uh, but you dip it in various chemicals to form a biofilm on top. Now this biofilm is going to release antibiotics at a constant rate, and once those antibiotics are released at a constant rate, as well as that biofilm is staying intact throughout the duration of the surgery and the patient's recovery, there is not going to be an infection. And we did the test for that. Next is, you're making a hip implant, but what is the structure, what does it look like on the inside, what does its cross section look like, right? So its cross section looked like this. This structure is known as a triply periodic minimal surface. So these are mathematical surfaces of minimal surface area. So these structures were designed on CAD, and they were put into the 3D printer. And when the printer printed the hip implant, its cross section had this internal structure. Now these structures have been borrowed from nature itself. No, we did not come up with those. When you put a microscope on a butterfly's wings, that is the structure. If you take a soap bubble, like a bubble that you make out of soap, and you look at its internal structure, this is what it looks like, right? And even if you take normal subchondral human bone and look at it under a microscope, this is what the structure of the bone looks like. This is how the osteoblasts are arranged, right? So we are taking inspiration from nature itself and trying to build products that are as close to nature as possible, so that they have the right stress shielding, they have the right they have the right gaps and holes between each cell, so that osteoblasts can sit inside those and proliferate. So that is why the structure was chosen. Next was, this was a very interesting brainstorming for us, is to what element to use, like what material to use. And as a material science guy, everyone was relying on me for deciding what kind of material to use. So generally what we use is, I don't know if you guys are aware, but when we say titanium, at least in the medical industry or any industry in the world, when you say titanium, when you say this plane is made out of titanium, or this microwave is made out of titanium, it is not titanium, it is a titanium alloy, right? Ti6Al4V. It is a titanium aluminum vanadium alloy. Because pure titanium, we are under the impression that titanium is very strong. It is not. In fact, titanium is much weaker than steel as well. Okay, its yield strength is very low. Its tensile strength is lower than steel. When we say titanium is strong, we mean titanium alloy. We are talking about Ti6Al4V. It's also known as Ti6, right? So titanium alloys are very strong, and they are very biocompatible as well. That is why we use titanium. We cannot use titanium because it has very large grains. First of all, it has a very high melting point, more than 3000 degrees Celsius. When it cools down very slowly. And what happens when metals cool down slowly? They go through three phases: recovery, recrystallization, and grain growth. And the grain growth is very high, very large grains. That's what makes it very ductile. It's not a very strong substance. So to make titanium strong and without using alloys, because once the titanium alloy goes inside the body, it is biocompatible. But recent research has shown that aluminum and vanadium keep leaching out. Those atoms keep leaching out, and those atoms leaching out causes neurodegenerative disorders, and all it's a whole can of worms that it causes. So what my intention was to completely do away with that and use pure titanium. But if you make an implant out of pure titanium, it's not going to be strong. So this is where 3D printing comes in. So when 3D printing is used on pure titanium, the rate of cooling is 10 to the minus 7 Kelvin per second. So this is how fast something is cooling, because that laser is almost micro focused, and it's heating up one small particle at a time, two small particles at a time. And they cool down really fast, and when they cool down really fast, they have very small grains. So as students of material science, I am sure you guys remember the Hall patch effect. Grain size is directly proportional to yield strength, right? So once they cool down very fast, the grain size remains small, and the overall material that you get is very strong. So this was kind of a breakthrough. Another thing is, this is basically the design. It's a trapezoidal cross section, and we use a lot of simulation software. We use a lot of FMEA. We use a lot of finite element analysis to make sure that our design is as close to natural bone as possible. And finally, we develop a prototype, and that prototype then goes ahead and gets FDA clearance. FDA is a body in the United States government known as the Food and Drug Administration, and they clear implants, and they clear anything that goes into your mouth or your body as a consumption, as a drug, or as an implant. And you have to have your product cleared by the FDA to be able to sell it or to be able to market it, right? So this is basically, I wanted to illustrate this project because I wanted you guys to understand the process of developing a new product. Okay, so I hope you guys found this interesting. Okay, next. Yeah, now here comes the interesting part. So mechanical engineering and what are its future prospects, right? uh, Most important thing that I'd like to bring to your notice right now is, if you look on the left, this is the median income of mechanical engineers within the nuclear and academic training. So nuclear industry is obviously something Indians cannot work on in America, at least, or any immigrant cannot work on. And nuclear, space, aerospace, defense, these are industries we cannot work on until we become citizens of the United States, right? So, but still, these are the median salaries. So, I wanted you guys to take a look at salaries in California, salaries in Boston, Massachusetts. That's where I studied, Boston, Massachusetts. So, these are the salaries of mechanical engineers, and these are some of the highest salaries that you will see out of any field in the world. And it is very important to understand that the US is the largest marketplace for mechanical and materials engineers, with the highest median incomes anywhere compared to any other place in the world. The field of material science and technology, where these two meet, technology as in apna Google, Facebook, Apple, Intel, AMD, all these companies combined with, where they meet with material science, that intersection is the most highest paying uh, industry in the world, right? Because you work with computation, you work with software, you work with things like machine learning, artificial intelligence, predictions, pattern recognition, language processing. This is where material science meets technology, and that small niche area is money making business. So you have to, if you want to make a lot of money, try to get yourself in that area, right? Like I said, unfortunately, areas like aerospace, space, defense, right now they're not open to immigrants due to the laws. Once you get a citizenship within the United States, you can work in areas like aerospace and all. Very important question that I get from a lot of students is like, should I get, if I'm a bachelor, like, should I get a master's degree? 100% you should. There is no question about that, because the standard of jobs, the difficulty of interviews, and the competition among engineers, especially in our field, has gotten to a point where you have to stand out. Okay, next question again is, should I, if I'm doing a master's, or if I'm already planning to get a master's, should I get a PhD? Now that is a very complicated question, and for that I will have to ask you a few more questions to be able to tell you if you should be getting a PhD or not. So we will touch these points later in the presentation. So I just wanted to motivate you guys as to, if you're thinking that there is no money in material science or there is no money in mechanical engineering, that is not true. This is recent data that I have lifted from the US labor website. So this is 100% accurate, and this is the kind of money that you could make. And it's a very rewarding field if you're in the right place, and if you're at the right company, and if you're doing the right things. It could be a very bad job in a very bad company making very less money as well. So this is where your approach comes in, right? There are computer science majors. I know people back in India. I have friends from back in school who who did a computer science major, and they're still making 3 lakhs a year at Infosys or something like that. So, and there are people who did the same computer science degree who are making buckets of money here in the US. They also studied computer science. They had the same, pretty much the same curriculum. Where is the difference? Is there a difference in their colleges? Is there a difference in their college rankings? Is there a difference between their IQs? Is there a gender difference? What kind of difference leads to such huge wage gaps? That is something we will address in coming slides. Next. Can you discuss the issues with hip implant? Yeah, definitely. One of the issues that I spoke about was the material selection, right? Material selection, as in, should we use titanium alloy or should we use pure titanium? So we had to do a lot of brainstorming. Another thing is, should we what kind of design we needed to use. So there is a lot of iteration that goes on, and this was just a small overview that I gave you. But how it happens is, when we work as a research team, when we work as a group, we brainstorm ideas, all of us come up with our unique approach to the problem. First thing is problem identification. Design nahi ban raha hai. There is no design right now. We have the material selected, we have the process selected, there is no design. Now 5 members of the whole team are going to come up with their own design, and we are going to run simulations, and we are going to rank them, how to which one of them has the least stress, and which one of them is as close to natural bone as possible, right? And we compare it. We do a comparative analysis. We do analysis known as SWOT analysis, right, for each and every implant: strengths and weaknesses, opportunities, right? So we employ these tools to make better decisions, because tools make better decisions than people. Because human beings have something known as implicit bias. Knowingly, unknowingly, you will make wrong decisions based on the biases in your mind. That is why it is more important to rely on tools. So just make a tool based comparison. Like, we use finite element analysis softwares, right? That compare the stress zones, and the software is going to tell you which is a better fit. You don't have to make a judgment. So these are basically a lot of issues that come with new product development, especially with hip implants. Another thing that you need to keep in mind is, these are implants that will go into people's bodies. And one big problem with the medical device industry is lawsuits, right? You make an implant, you sell it, goes into someone's body, they die, or they get infected, or something happens, you have a lawsuit on your hands, right? So for sure, especially in the US, definitely have a lawsuit on your hands. So it is very important that your due diligence is is extreme. This is why we do a lot of pre-application due diligence. After that, we apply to the FDA, and then the FDA does its own due diligence, which is very strict. And after that, only your product comes into the market. Even then, people die. So yeah, the those are basically the main challenges. So the challenges are, more broadly speaking, to stay within the limits of the FDA. The FDA has certain guidelines, and you have to develop your product within those guidelines. So yeah, and if you want to know this in more detail, feel free to message me. Yeah. So yeah, another important question. Speaking of careers and colleges and salaries and all these things, do college rankings matter? Definitely, 100%, no question about that. And I'm not saying this is not an opinion. The latest study suggests that graduates from elite universities definitely get paid more than they are worth, especially since a graduate from a top 10 engineering school performs only 2% better. So I'm not saying that a high ranked college will teach you better than a low ranked college. It's pretty much the same. Science is going to stay the same, right? But I can guarantee you that somebody in a higher ranked university is going to make more money than someone in a lower ranked university, simply because of the kind of opportunities, the kind of networks, and the kind of doors that open with that name being associated to your name. So I have been fortunate that I have been associated with IIT Kanpur from the very beginning, from my bachelor days. So I can I can tell you a number of times a lot of doors have opened, a lot of opportunities have gotten, and I'm very sure that there are many students who are at the same level, who have the same, maybe even more experience, right? And they are not smarter than me or stupider than me, but are pretty much at the same level. But I'm very sure that I will get that advantage, I will get that interview. Very good question. How I'm going to get to that internship part soon. Yeah. So yeah, so I know I have gotten that advantage, and I know people from top schools like Northeastern, Northwestern, Harvard, Princeton, Yale, Stanford. These people get that advantage everywhere, and not just in terms of life and in terms of career. You basically get it everywhere. Plus, all the people that were from your batch, all the people that you know, all the people that you worked with, these people are also going to become other successful people in different walks of life. So you generate a network of success, and you can use the success of others to fuel your own. So if you want, let's say you're working in a company or in a research group, and you require funding. And if you are from a small university, first of all, the NSF or any other funding agency is not going to fund you. But let's say you're from Stanford and you're struggling for funding, you can reach out to alumni who's probably the head of the NSF or who is head of a journal, and they are going to give you the funding and they are going to sanction that funding for your research group. So that you are successful. So it's not just about what you learn at a university is the kind of what's important is also obviously what you learn is important. Apart from that, the value the degree holds, right? The value that degree holds is not just in terms of how much money you can make, it's also in terms of what networks you make, what kind of an alumni network there is, right? For example, Harvard University gets an endowment from its alumni for about I think $4-5 billion per year, which is huge. They are not funded by the government. They're not funded by anybody else, just by grants, only by alumni. That that shows you how far their alumni have gotten. So it is if somebody tells you that college ranking doesn't matter, that is just a happy lie people tell themselves when they don't get into colleges. So college rankings do matter. And next question that I get a lot is, okay, how do you measure success? Like, are you successful if you got into a good college or a highly ranked college, or are you successful if you're making a lot of money? So I think I have narrowed it down to this definition. I think success as far as a work setting is concerned, or as far as career is concerned, success is basically a combination of personal satisfaction, financial stability, and intellectual challenge. Even if one of these three, I think, and at least for me, if one of these three is not being satisfied, then I'm not doing a successful job. Even if I'm making a lot of money, and even if I think I'm satisfied, but if it is not intellectually challenging, not a good job. If it's very intellectually challenging and very satisfying, but there's no money, so that is not a good job either. So you have to find that right balance, and sometimes it is difficult because there are so many companies, so many organizations in the world you can work for. So finding that right balance, that's the trick. Next slide, please. Hybrid additive manufacturing. Okay. Okay. Hybrid additive manufacturing. I think I'm assuming you're talking about additive as well as subtractive. If you can clarify that, okay, I can answer you better. Okay, so moving on. These I was just thinking about making this present. When I was making this presentation, I was thinking about the most important tips that I've given to people, and the most important tips that I have received, like as a student or as somebody who was looking for a job, who's looking for opportunities, right? These are some of the most important things that I narrowed down to, and I just put them here. First thing, coding is not only for serious graduates, it's an essential engineering skill. If you are not learning coding right now, if you have not learned, please start. Start with Java, start with C++, start with Python. It is extremely important, not only because you will get job opportunities, but a lot of work in mechanical engineering, even in biotech, even uh, in everything is done using software, because it's just more efficient. And if you are not good at using that as a tool for your work, then that puts you behind in the competition. Learn to use software as a tool, right? For example, let's say even if you have a data entry job, right, you just have to copy paste something from one folder to another folder. But if you are able to make a Python script that does it automatically, you will be outperforming everybody else, because you have learned to use software as a tool. So please start learning software if you have not learned just basic coding skills. Learn how to work in object oriented programming like C++ or Java or Python. Python is very easy to learn. Put in a couple months, join classes, or I think there is W3 schools online which will help you learn, and it is going to seriously be a huge addition to your resume, not only for jobs or for research. It is very important in research as well, uh, but as well as for expanding your knowledge and for expanding your skill set as an engineer. So it's another tool in your arsenal at your disposal that you can use to solve problems. Software is used everywhere from economics to the finance industry to the stock prediction industry to biomaterials, mechanical, aerospace, everything, all kinds of simulation software, everything uses basic coding. So please learn that. Next thing is data analysis and visualization. Just like software, being able to make sense out of numbers, being able to use things like probability and statistics, very important. A lot of us, I think, as far as I have seen in material science and mechanical engineering, the course structure in Indian colleges do not make these courses compulsory, like data analysis and data visualization. These courses are not compulsory, so a lot of people don't take them. But as far as I've seen in industry, I have not seen one industry that doesn't use these techniques, doesn't use these things. So I had to learn on the fly while working. I had to put in those extra hours, but that's what college is for, right? So while you are at college, try your best to take these courses if you haven't, and try to learn things like data analysis. That includes R Shiny, SAS, that could include things like and all of these data analysis tools, visualization tools like Tableau, Power BI, very important tools. Again, tools in your arsenal to be a better engineer. Next thing, the decisions that you make today depends on where you want to be. So be clear about where you see yourself 5 to 10 years down the line, and make today's decisions based on that. Ask yourself where you want to be. Do you want to be a rich guy driving a sports car? Not a bad dream to have. Very, very amazing dream to have. Rich guy driving a sports car. Great. Now to be able to reach that point, what kind of a salary would you need to afford a Lamborghini that costs 120 $130,000, even a basic one? And that is basically almost 50% of your yearly pay. That is the rule that finance uses to calculate net worth. So if you're buying a $150,000 car, you should be making at least $400,000 a year. Now, to be able to get to land a $400,000 a year job, these are the fields that you can work in. This is how you make decisions today. To be able to get into that field, this is what I should be able to do. If I want to get into this job, these are the skills I need, and to get these skills, this is a course I should do. So your journey from a student in India sitting in his hostel to driving that Lamborghini on a Miami beach begins by deciding to register for that course. And if you are not making these planned decisions, then you're just making life more difficult and unpredictable for you. So please keep in mind, right planning is always important. Another thing, at least when I was at IIT, a lot of my seniors and a lot of the people who were with me told me that CGPA is not important. It's okay, it doesn't matter. After your first job, nobody cares about it. Total lies. Your CGPA is more important than you think, because it is the first filter. Yes, CGPA is not important, because just because you have a good CGPA doesn't mean you're a good student, doesn't mean you will be a good employee. But if you have a bad CGPA, it definitely means you're a bad student. So remember that CGPA is not a selection criteria, it's a rejection criteria. Right? Just like that, if you want to get into colleges in the US, you give an exam called the GRE. GRE is not a selection criteria. You get full score on a GRE does not mean you'll get into Stanford. But if you get 310 on a GRE, it definitely means you're going to get rejected. So it's a rejection criteria, it's not a selection criteria. So companies will just shortlist your resume based on your CGPA. If and they make tiebreakers based on CGPA. If there is another candidate going for the same job, pretty much same interview, just like you, same level, do they choose you or do they choose him? So this can be a small factor. He was a 7.5, you're an 8.5. Okay, they'll give you the job over him because you have something that is an edge. So don't ever let anybody tell you that CGPA is not important. It is, as long as you're a student, and for many years, even after you're done being a student, it is going to be important. It is going to be a deciding factor for so many other things, not just jobs, so many other things. If you get a funding for a research or not, if you get that PhD position or not, what kind of college you will go to, if you will get a scholarship or not, uh, and that makes a huge difference in your lives, because if you're applying to a college in the US, you might lose out on a scholarship because your CGPA is low, and your parents will have to pay 30 lakhs more for your education only because you didn't do well in one course. So keep that in mind, and study hard, get a good CGPA. And getting a good CGPA is not difficult. Do your assignments on time, study well, and get that CGPA, because it is going to take you a long way. Does not mean that if you get a CGPA, does not mean that you are a good student or you have a grasp of concepts or anything like that. But if it's bad, nobody is even going to ask you that question. So put yourself in that position, right? Next, coming here, this is what I was talking about, and this is the question I got. Do as many internships as possible. Vacations are meant to be productive. I did as many internships as I could. uh, during my time as a student, every December back at IIT, every December we got a break, a winter break, and summer we had almost 3.5 months of break. So I have utilized each and every vacation period that I got, even during my master's degree and later, whenever I got a chance. I did an internship. I went to Egypt for one of my first internships. I worked at my dad's a scientist back in India, so I worked at his lab just to get myself started off in a comfortable setting. What to do in a lab, how to behave in a lab, what are the protocols, practices. I worked at a nitrogen plant there. Then I started doing more complicated things. I started going to organizations, asking them for internships, sending emails to professors asking them for internship. Finally, I got a chance to go to, after my graduation, I got a chance to go to Europe for another research assistantship. Before that, during my undergrad, I worked at BARC, Baba Atomic Research Center, that's in Bombay. I worked for DRDO in Hyderabad. We worked on super alloys, on nickel based and iron based super alloys. Oh yeah, sure. So I did an internship at BARC as well as DRDO. So BARC basically, I was a student of material science, and I did a lot of metallurgy at the time, right? In India, material science is pretty much close to is the same as metallurgy. So a lot of colleges have just changed their name from metallurgy to material science, because it would fit a lot of job roles. So I was working a lot with metals at BARC. Very nice atmosphere. So some of the best, most brilliant people in India work at BARC. And I think I worked on martensitic phase of stainless steel. And we tried to understand what its corrosion was like, because BRC designs nuclear reactors, and a lot of their stuff is made out of stainless steel, the internal components, and they get corroded over time. So our group's job was to figure out the rate of corrosion and how it can be prevented, what techniques can be utilized in a safe manner, that can be deployed into these nuclear plants, so that these steel components will not corrode over time. So very interesting project. Then comes to DRDO. I'm not at liberty to discuss what that project was because it concerns the defense. But I can tell you the material that I worked with was a nickel based super alloy. Very interesting stuff. I don't know if you guys have studied this. I'm pretty sure you must have. So how super alloys are made. It's a whole universe in itself. Lots to study. So yeah, it was amazing experiences, and I would urge you guys to apply to these places. These places have an application system. You go to their websites, you talk to their people, reach out to people on LinkedIn. You will come across the application process. You just have to pay a small application fee, fill out their form, send them your resume. Sometimes you have to even take an interview, and yeah, if you work hard, you get these positions, and these positions stay with you. And anywhere in the world, when anybody looks at your resume and they sees that you have worked for the Indian defense, you have worked for India's only government sponsored atomic research organization, it sets you apart from the rest. It sets you apart from all those people who have done their internships in Wipro, TCS, Infosys, and just for the sake of doing an internship, it puts you in a whole different league. So try to get into that league, and for that you'll have to work a little hard. Okay. Next thing is, yeah, a few more tips. Surround yourselves with high achieving mentors and high achieving peers, because you are only as good as the company you keep. Okay. Another saying that I go by is, if you're the smartest person in the room, you're in the wrong room, right? So do, don't be the smartest guy in the room. Surround yourself with guys smarter than you, much better than you. You know for sure these guys are better than me, and this is what keeps you in that environment. It keeps you in that competitive spirit. It keeps you learning from these people. It keeps you trying to emulate what these people do. What are these people's achieving habits? How is this guy achieved so much at this age? Why am I not being able to do that? So sooner or later you inculcate these high achiever habits. You inculcate work ethic, and so many you get to learn, you get to make networks. So very important is, basically I'm saying, is network, and network with people better than you. Next thing is, understand the research and industry trade-off. Very important point. I'll keep it short now because we've been going for too long now. So research and industry trade-off. Basically, research has very high standards but makes no money. Industry has low standards as far as the work is concerned, makes a lot of money. So understand where you want to be in life, and sometimes you can even be in between. If you go into research, do not think that if you get a PhD degree and there's a doctor in front of your name, and all of that, you're going to make money. No. uh, PhD graduates are some of the least paid people in the world. If you can look at the data online, sometimes even bachelor students make more money than PhD graduates. The reason is that PhD is very focused. It puts you in a very small industry. And for example, I'll give you an example. This pertains to one of my friends. So let's say you did a bachelor's in material science, master's in mechanical engineering, material science, whatever, and then you did a PhD uh, in the motion of some superfluid, or some hydrodynamics or something like that. A company like Tesla is not going to hire you because you are considered an expert in fluid dynamics. They have nothing to do with that, and they are an electric car company. But and you are an expert in fluid dynamics. Nobody is going to hire you for, because they don't need you. But if you are a master student with this, and if you had not done that PhD, you are a master's in mechanical engineering, they can find a job for you very easily. Anywhere in the chassis building, in the tires, in the battery pack, anywhere, any of those regions, you can find a job, right? So do not make yourself an expert in one thing so much that all the other industries get close to you. And if you have a bachelor's in material science, try to get a master's in mechanical engineering, because mechanical engineering is much broader. It opens up avenues for you. It opens up industries. You can work at SpaceX. You can work at Tesla. You can work at Intel. You can work at Google. You can work at Facebook. You can work at some company that is making some implant. So all this huge range of jobs are open to you. If you don't like it here, you can switch. If you don't like it there, or you don't not getting enough money, you can switch to find the balance. But if you are in a very niche, very small industry that hardly has a few companies to even begin with, then life becomes very difficult, and being able to switch becomes very difficult. So always remember, keep your area broad, and if you are going into research, then there is no turning back. Once you get into research, you cannot turn the clock back and try to become a generalized guy. That's not going to happen. And do not be under the impression that you will make a lot of money if you do a research. So I have a friend recently, my previous roommate, who did a, a master's degree from a very good university, uh, postdoc and PhD at a very huge university in the US, in Boston, probably ranked one or two, number one or two in the world, right? And after all that, the job offer is less than one third of what a master student makes in the US. So it is very sad that people spend so much time, 6 years, 5 to 6 years PhD, 3 to 4 years postdoc, 3 years postdoc, 2 years masters, and 4 years bachelors. That's almost 2 decades of your life in studying, and then you are being paid less than average. So do not put yourself in that position. Another thing, that this is my next point, is also regarding that. If you decide a future in research, it is good, it is noble, and if that is what makes your clock tick, and if that is what is the passion of your life, is doing research, go for it. It's great. but understand its limitations and boundaries. You cannot complain that your salary is not high. It's not good when you're a scientist. Okay. Another thing, material science, software P grade or materials grade, US salary. Okay, so you want to know the salary difference between software and so in Intel is basically a semiconductors company. So obviously the guys in hardware get paid the most. Software guys get paid everywhere. Software guys get paid a lot, but like I said, the difference is not significant. So uh, the difference is not at all significant. Software and hardware get paid pretty much the same. Software will get paid a little bit more in any tech industry, but that difference is not significant. So that difference is maybe a few $1,000s, which does not amount to anything as such. So being in the right industry is very important. uh, Another thing, since that person asked me about software, is it is I think it's a known fact that the software engineering region is the highest paying region in the world. Google hai, Facebook, Netflix, Salesforce, these companies pay the highest salaries to their software engineers. But we are not from a software background, we are from material science, we are from mechanical, right? So we have to find that sweet spot between software and material science. Where does that meet? That meets in a few places. They meet in the semiconductor industry. That's what I do. Another place they meet is computational material science. So if you use techniques like machine learning, uh, artificial intelligence, neural net building, all of these techniques to find new atoms, to find new combinations of alloys, to develop new materials, to understand how fluids move in a certain medium. So if you use computation, basically computer science or math, to advance material science in some way, then you will be making the same amount of money. It's about deciding the right field, placing yourself at the sweet spot. That is what's important. Next thing, the right attitude is more important than a positive attitude. So a lot of people, a lot of motivational speakers, a lot of different kind of people are going to come to you and tell you be positive. I don't even know what that means. What is important is being right. And being right, how do you be right, is to have a logical approach. Like I told you that Lamborghini example, if you want to have that end goal, you have to make rational decisions to increase the probability of you getting to that goal. If I take this course now, I'm going to get this degree. If I get this degree, I can apply to, my probability of getting into these companies is high. If I get into this position, this will be my salary. And if I get this salary, I can buy this car. So making those kind of rational decisions, that is very important. And not every time being positive, I don't even know what that means. Being right is important, and being rational and being logical is important. And that is what you need to do if you want to achieve any semblance of success. Next is choose your geographical location, and based on your decision as to what your career is going to be. So if you want to work in automobiles, you have to be in Europe, because that's where the best work in automobile happens, or Japan maybe. If you want a career in biotech, or if you want a career in semiconductors, the US is the place, right? If you want. And one of the last tips that I want to give you is make a LinkedIn account. Surprisingly, a lot of Indian students I have seen that I reach out to, or who reach out to me for help, they do not have LinkedIn accounts, and I'm very surprised, because here everybody and their mother has a LinkedIn account. So please make one if you do not have it so far. Next. Yeah, these are very important things. Important material science specific areas for jobs. This is specifically for jobs. Like I said, first one, semiconductor and hardware industry. Second one, 3D printing and additive manufacturing. Third one, medical device, biomedical engineering. This is all about making your implants, making your catheters, working for large companies like Johnson and Johnson, Medtronic. Very good work, very noble work. You're basically saving lives, and very high pay, good stuff. Next is manufacturing and industrial engineering. I have a very close friend who currently works for a drone making company. Very interesting, very exciting, and uh, good pay. Everything's good. So these are the industries that you need to target based on your skill set, based on your interest, and based on where you think you would do well. Areas to stay away from. A lot of engineers stray away from engineering and get into these areas: project management, engineering management, construction, real estate, or structural engineering, iron and steel industry. These are good, obviously, good industries, but again, they have their own problems. If you want to know in more detail, contact me. But it's either low pay, low number of opportunities, or they're just those jobs are just basically not interesting. And last one, the iron and steel industry used to be a very good field to work in, but it's largely getting automated now. It's basically very soon. I think in 8 to 10 years, nobody will be working in a steel industry because it's completely going to be automated, completely be run by machines and robots. So human beings don't need to work in the steel industry anymore. So if you go into that industry, there's a huge chance that there will be pay cuts, there will be layoffs, and you might be losing your job sooner or later. So these are the areas I would advise, in my opinion, to stay away from. Next, important areas for research. So despite everything I said, remember that research is amazing. It is very important, and that is how science proliferates, because we have researchers, we have scientists, right? And this is how industries are built. And yeah, a PhD scholar might not make a lot of money, but you might be able to, you might develop something, you might bring out a patent on something that is huge, and you can build your own company, and that might be worth billions of dollars or millions of dollars, right? So yeah, so the risk with doing a PhD is either you make nothing or you make a lot. So it's like that. So important areas for research are, like I said, machine learning and artificial intelligence for computational material science. Google this. If you don't know what these things are, ask me. Google them, or try to read something on them. And if you don't understand what they are, or if you want to know more, please feel free to message me. Okay. Next thing is biomaterial development and biocompatibility generation. This is what I used to work on for a long time. Next, materials for stem cell research. What, again, this is another deep topic. If you want to know, contact me. Stem cell research, very important area for wound healing and curing diseases. Next, nanotechnology for medicine and semiconductors. Like I said, excuse me, nanotechnology working at small length scales for medicine and semiconductors. Very important area for research if you are interested in being a successful scientist. Next, please. Yeah, these are some of the most important FAQs that I get from students and other people who I'm in touch with. First thing, should I study in India or abroad? In my opinion, in my humble opinion, please study abroad. uh, there are very few Indian universities that have the infrastructure. They definitely have the best people, but they do not have the infrastructure or research funding to be able to do work that is important at a global scale. So please study abroad. Next question that I get is US, UK, Canada, Europe, Australia. Where do I study? That depends on which area you want to work on. Again, where you see yourself 5 6 years down the line. If you want to work in biotech, or if you want to work in biomedical, if you want to work in automobile, which area do you want to work on? This will decide the country that you want to work in. And as a safe option, I would suggest US is the best as far as almost any industry is concerned, right? Because there are more opportunities here than there are people. So you figure. Next, very common, very important question. My family or I cannot afford to study abroad. What do I do? Obviously, so the amount of capital required to be able to do a master's degree in the US ranges from 40 lakh Indian rupees all the way to 80 lakh Indian rupees, right? They can be plus or minus a few lakh on both ends of the spectrum. But yeah, that's the range, right? And depends on what kind of university you get in. So if you get into Harvard, the fees are going to be over 1 crore. But if you get into something else, it might be like 28 lakhs maybe. So it depends on college, it depends on state, it depends on how you live, it depends on which city you live in. So all kinds of factors are involved. That's why the range is so huge, right? But still, even that kind of liquid asset is very difficult for an average Indian family to be able to afford that, to for the education of one person, right? A lot of us might be having brothers and sisters, and we have to be able to provide for them as well. So what is the way? And I have counseled and I have helped a lot of students through this. So there are ways. If you are restricted by finances, you should not be restricted for your education. There are so many ways you can get this done. You can come to the US. I mean, I know people who have studied with me in the US and have been able to pay their fees by these means, even though their families uh, come from a lower middle class demographic from India. So don't think it is impossible. It is possible. How to do it? What are the steps? It's very long. If you find yourself in that position, and if you think you need some tips in being able to manage the finances for a further education, let me know. I can be of help. Next, what is the scope of jobs in the India market? Very important question. And how skewed are Indian salaries? uh, I decided to come here. I decided to switch countries because first thing, I did get opportunities. Second thing is, I saw the salaries, the way people from my batch, people that I studied with, work with, what kind of salaries were they making? What kind of job work, job life balance did they have? What kind of lives they were leading overall. And honestly, I was not satisfied. I was not happy with what I saw. And Indian salaries are very skewed. I mean, you will see, obviously, you guys from NIT, right? So you might be hearing news about what some NIT guy made 1.5 crore package, IIT guys make 1.5 crore package. Those are basically US jobs, which are 120,000 US job, which is entry level salary in the US. And it is just translated into rupees and it is shown. And that really doesn't mean anything. It's not a very high salary, it's an average salary. And so don't get scared by those numbers. I'm sure you guys know all this by now. But if you do not know, or if you still believe those numbers, or you think that somebody is making that kind of money, you can contact me. I can explain it to you how this works in detail. But yeah, Indian salaries overall are very bad. Most of my friends were making 6 to 8 lakhs per annum, 10, 12, 13, this range. And at IITs, these are still much higher than what people make from other colleges. I saw, my house is in Hyderabad, Andhra Pradesh. So I'm originally from Bombay, but we moved there. So my friends who were in Hyderabad were working for TCS and Amazon and all that, and making 2 lakhs, 1 lakh per year. I've seen 1.5 lakh per year. I'm like, is that even a salary, right? So for engineers, salaries are very bad. The reason is that a lot of companies in India are not homegrown companies. Oh, very good. Good question. I'll get to that. Yeah. So a lot of companies in India are not homegrown. A lot of companies in India are outsourced branches of American or Chinese companies or Korean companies. So if you're working at Amazon India, you're not working at one of the world's most expensive, world's most successful and largest companies. You're working at their subsidy in India. And all of Amazon Hyderabad's large building, one of the largest offices in the world, it's basically a huge call center. So when you in the US, when you tell somebody that you work for Amazon, it is very prestigious. But in India, if you tell somebody that you work for Amazon, that impression is, oh yeah, 2 lakh package. So that is the skew. That is the difference. And jobs in Amazon in the US begin at $140,000, which is 1.5 crores basically, or more. So that's the difference. And in India, jobs begin at 1.5, 2 lakhs, 3 lakhs, 4 lakhs, 5 lakhs. That's it. That's what people, and maybe the higher level managers or someone like that, senior managers will be making 20, 25 lakhs. That's it. And if you're performing well and if you show promise, they will just transfer you to Amazon Seattle. But if you want to stay in India and want to work in India, you are confining yourself to a marketplace that is outsourced, completely outsourced, because we don't have our own companies. And even if we have our own companies, our currency and our country is not in a state to be able to pay those kind of salaries to people. No matter how good, even if you are a magician with code and you are extremely good at what you do and you want to work in software, The highest possible salary that you're going to get is 30 lakhs per annum in India at the best company. Obviously there might be outliers, but yeah. And I just got a question as to why did I decide to go into research. So yeah. So after my fourth year, after my final year at IIT, I did sit for the placements. I got placed at Schlumberger, which is one of the world's largest oil drilling companies. And then they needed me to go offshore somewhere to work, but and the salary also was pretty good. They were offering, as far as I remember, that time it was, I think, 32 lakhs per annum is what they were offering. But I thought I could do better, and that field is something I'm least interested in oil drilling, and that is not where I wanted to put my efforts. And I got a lot of opportunities. I graduated in 2017, and then I got an opportunity to go to Europe for some research. And I thought that was way more exciting than working for a company drilling oil. So yeah, for somebody else, that does not mean it's not a good company or it's not a good job. For somebody else, that might be very interesting, and they're welcome to do that. But that it just didn't interest me at the time. So I moved to Europe. I did a lot of very good research there, got to travel a lot. It was fun. I got a very nice stipend. So I didn't have to ask anybody for money. I could just roam around the country, uh, 26 different countries on a Schengen visa, right? So it's a lot of fun. It's very exciting. And very good research, very good work, a lot of good results. And a lot came out of that. I'll talk about it later. Okay, next question that which is important is yeah, I heard that CS grads make more money. Can I switch? Definitely, you can switch. If you think that you are in a field, you've completed your bachelor's, you cannot switch your degree. That is not true. You can. If you think that you did a bachelor's in material science, mechanical, and you cannot get an admission into any other field in a different country or whatever, that's not true. You can definitely get it. Okay, it just depends on how you apply. Next, material science doesn't interest me. Should I switch? Definitely, you can switch. Same answer as above. You can switch. Nobody's going to stop you from switching. A lot of people, even I used to at one point think, ki, I'm stuck in this field now. What do I do? I don't like it here. I don't like this area. A lot of my civil engineering friends used to think that they wanted to get out of that field as soon as possible. What do we do? You can switch very easily. It's not difficult. It's just a process that you need to follow. Next thing, material science does interest me, but I want to work in software. What to do? I answered this question before. Work in fields that are the intersection of materials as well as software or technology. So work in computational material science, work in semiconductors, two very important fields which are basically the intersection of software and material science. Software. So the field that I work in is actually software of three. It's a integration of three fields. It's material science, it's electrical engineering, and software engineering. So I get the best of three worlds. Yeah. So another thing, what is the situation of women in STEM? So STEM basically stands for science, technology, and engineering and math, right? A lot of girls, a lot of females are apprehensive about continuing their education in a foreign country, or continuing their education in sciences or engineering. uh, Definitely, because it's completely a male dominated industry, but things are changing, especially in the US. We constantly put more efforts to hire women, to hire inclusive and diverse people from different walks of life, different backgrounds. And the gender balance at work is very good, especially in the US. And I don't think I can say that for India right now, but in the US, the women in science are very interesting, very successful. They are doing very well for themselves, and they are being paid as the exact same as men are being paid. So all those doubts and apprehensions that a girl in India might have as to continuing her education, or professionalism in this field, should not be thinking about that, especially if you're deciding to move to the US. Another thing is, I'd like to, if whoever are the girls listening to me right now, I'd like to encourage them towards science and engineering. And we definitely need more women in STEM. And a lot of my friends who are girls, who are women in STEM, are some of the most bright, intelligent, and successful people I know. So it's very much important, especially in a country like India, that we encourage this. Next question is, what it is to like to work in the US compared to other places? Definitely very different, much more challenging, because the US is the hub of science and technology in the world. I live in Silicon Valley right now, which is the, which is which is the heart of innovation. Just next to my building, our office, my Intel office is right here, and then a few miles away is Google, Facebook, Netflix offices, and so I'm constantly surrounded by people who are trying to innovate, right? And constantly surrounded by a great team of diverse people in my team at work. Right now I'm not working from office, I'm having to work from home due to COVID. I hope to return to office soon. But all the people I interact with, they come from different walks of life, uh, different countries, different people. So the office balance is amazing, the amount of leaves that we get is amazing. The benefits that American companies provide is is a lot compared to anything in India or anything anywhere else. I mean, in terms of leaves, I think US gives more, I think Europe gives a little more leave, but still, uh, as far as Intel is concerned, Intel provides uh, education benefits. Like if I want to do another master's degree, if I want to do an MBA, I'm myself planning to do an MBA, or maybe 1 or 2 years later, just to mix things up, just to understand business aspect of things, and Intel will completely pay for it. Intel is going to pay for all the fees. If I go to Harvard or Stanford, the fees are over 1.5 crores, completely sponsored by the company. Next thing, Intel provides benefits like food in the office, laundry in the office, dry cleaning in the office, completely taken care of. A lot of company discounts, a lot of other benefits, like there is child care, there is dental insurance, there is health insurance, there's vision insurance. Everything is 100% covered. Anything happens, it's completely covered. Families are covered. As far as Intel is concerned, even IVF, if there's a person who's trying to raise a family and is unable to have a child, Intel also pays for the IVF treatment. So I think it's beautiful that companies in the US not only care about the kind of work their employees provide, but uh, they also care about the kind of life they give to employees. So you give the company your work, and the company gives you your life. So it's pretty awesome. Okay, what is Six Sigma Yellow Belt certificate, which is mentioned in your LinkedIn profile? So basically, Six Sigma is very good question. Very one thing I forgot to include in this. Six Sigma is a way of measuring how efficient a process is. So if you Google that, you will understand that there are different levels to Six Sigma. So I just did a small training and a small project back in my university that got me the yellow belt. So to get to the next level, you need to do a green belt certification. After that, you need to do a black belt certification. And if you have a Six Sigma green or black belt, that will seriously help you get higher paid jobs. Yes, but those are important only if you're like a process engineer or somebody who works with processes, like step 1, step 2, step 3, step 4, and then finding out that what are the discrepancies, finding out if there is a target you're trying to hit, how far it is. So these are called standard deviations, right? If there are so many results and I plot them on a graph and I get a bell curved graph like this, that is known as a normal distribution, right? And the center is the mean. And how far the center, how many standard deviations I'm away from the most common factor, which is the top of the graph, that is known as a sigma. So that is 1 sigma, 2 sigma, 3 sigma, 6 sigma, right? So that defines process efficiency. So I wouldn't like to get too deep into that right now, but yeah, if you want to know more, message me. Next slide, please. Yeah, these are some of the most important resources I wanted to share with you guys before I leave today. uh, these are resources that have helped me, and I think they will help you too. I didn't know if you guys know about these things, but you should. First one, levels.fyi. It's a very important website that helps you see actual salaries of people that were offered to them throughout the world at different locations and different companies. Definitely take a look, gives you an idea what to expect. Next is teamblind.com. Go to teamblind.com. You can even use the Blind app, make an account. It's basically LinkedIn, but anonymous. It's basically baby between LinkedIn and Reddit. So it is for people discuss their interviews, people discuss their company knowledge, and a lot of other resources are shared here. So always take a look at this. Next thing is Sci-Hub. Sci-Hub is very important for being able to download scientific journals, papers for free. So generally, scientific journals and papers cost money. You're supposed to pay the journal to be able to legally download a research paper. But as a student, you cannot cannot keep paying for research papers all the time if you want to keep reading. So just go to this website, paste the link of the research paper you're trying to read, and this website will return a PDF of whatever paper you want to read. So very, very, very helpful. Next thing is this: there's a small add-on called Jobseer. Jobseer compares your profile to a job profile on LinkedIn that you're looking at, and it gives you a match index as to how much your profile matches to that job. That helps you decide if you want to even apply to this job or not, or how you need to change your profile in order to be eligible for that particular job. So very important add-on. All of these are free, by the way. None of them cost money. Nothing. Zero. Next is libgen.in. This helps you download books, novels, anything, any kind of book. Just type in the author's name or type in the title of the book. So the search bar in this website is very sensitive. If you make a small spelling mistake, it will say zero results. So make sure the exact name of the book you're typing or the name of the author you're typing, and you get a list of all the books written by that author or any all the books by that name, and you can download it 100% free. So yeah, these are some of the resources I wanted to share with you guys, because as a student these helped me a lot, and I hope they are helpful to you as well. Next slide please. Another thing, having good mentors and having good recommendations. So wherever I have reached so far, I think it's all thanks to the people who have supported me, people who have taught me, right? Most recently, most importantly, Dr. Webster. So he is currently my advisor, currently my guide and teacher, and he is one of the top 1% researchers in nanotechnology and material science in the world. Look up his profile on Google Scholar. You will see he has a research H index of 110. Like some people call him the god of nanotech in the world. So very successful guy, very huge name in the field, and that is very important. You have I look up to such people, and that motivates me to work harder, to do better work, to come up with better ideas. And these kind of people like Dr. Webster uh, are not only successful, but they are very encouraging. So it is very important to surround yourself with people like this. Dr. Barhoff, no, Dr. Barenberg is somebody I worked with at that hip implant project I did with him, and Dr. Gura forever. So my guide since my days at IIT. And it is important for you guys to maintain very good relationships with your professors. Right now, just because the course got over and you passed and you got whatever grade and it's over, does not mean that you never talk to that professor again or never look at him again. They are very important people. As students we might not feel that way, but trust me, later you will realize they are very important to you and your career, and at some point you will realize what they were saying was right. So when I applied recently, when I applied for my citizenship, it was my professors from IIT that gave me my recommendation. When I wanted an admission into the US, it was my professors from IIT that gave me a recommendation. So uh, and nobody's going to give you a recommendation if they don't know who you are. You just send them an email. Nobody's going to give you that recommendation if they don't even recognize you, right? So maintain very good relationships with your professors, do projects with them, talk to them, maintain a strong learning relationship, and that is going to help you out in the future. And you will learn so much from these guys have been in industry for 30-40 years, and try to soak up as much as you can, try to ask as many questions as you can, and try to get from them as much as you can, because they are there to give, and that is their job and your job, and you should do your job as a student is to learn as much as possible from your professors, because they are your only resource in school. And once you are out of school, once you're out of grad school or undergrad, whatever, you are out into the real world, and you're it's like you are in a very protected environment first, and now you're supposed to perform. So without proper guidance, it becomes very difficult to perform. And make sure you get good mentors. That's all. Next. So yeah, these are my contact details. This is my LinkedIn. This is my Instagram. So whatever, and if somebody needs to text me or ask me something quick, so feel free to get my number from Rahul. So yeah, thank you for having me. I think it stretched too long.
Thank you so much, sir. It was really a very good session.
Yep.
Now I would like to invite Tanya and Abhishek.
So thank you for your precious words.
Thank you.
Technology has paved the way for the multifunctional devices. It has
Yep.
made our lives easier, faster,
Yep.
better.
Definitely.
We really appreciate that you emphasize upon technology and healthcare.
Yep.
This is something which we really need and quite appreciated
Definitely.
from
Yep.
you.
Yep.
Can Tanya, I would like you to give a vote of thanks.
Thank you, Abhishek. Sir, we are very grateful for your time. Thank
Thank
you.
you.
Thank you so much. You
Yep.
told very important things that as material science student as first year student, we really needed that.
Oh, you're
Richard
in
Branson
first year.
said,
Are you in first year?
Richard Branson said, yes, sir, I am in first year.
Okay. Okay. Nice.
If your dreams do not scare you, they are too small. And in today's session, we have learned that dreams do come true. And we
Yep.
have got to the end of this closing event. I would like to thank our guest Aditya Morey sir for being with us today. Thank you all
Thank
the
you. Thank you
chaps
for
from our
having me.
team who made this event possible. Further, a final gratitude towards all of our audience who were there for us. Metamorph will be back soon with some other amazing events. Till then, take care everyone.